Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azfar bin Makjuhe. Today I will present about the final year project 2. The title is Investigation of Microstructure Properties for Motorboat Propeller using Modified LM25. My supervisor is TS Zulkarnain bin Marjum. Okay, we'll go to the introduction, which is the propeller is a main component for boat. Material of propellers such as aluminium alloy, stainless steel, copper alloy, nickel aluminum bronze, and manganese aluminum bronze. Mostly the outboard propeller are made from steels, copper, and aluminum alloy. The casting are used for mass production for reducing the cost. To reduce the deformities, need to improve the casting process. This study will focusing the microstructure behavior of both propeller and modified LM25 with adding copper and magnesium. Next, we go to the statement of purpose, which is to investigate and compare microstructure properties such as grain size and porosity between the both propeller, non-heat treatment, and T6 heat treatment of modified LM25. The problem statement is mostly the propeller are flat toe up, bent, and damaged. This is will reduce the fuel efficiency of boat, and it is need the specialist to repair. Next, we go to the objective, which is firstly is to compare the microstructure of LM25 aluminium with existing propeller. Secondly, to study the non-heat treatment and heat treatment of modified alloy. And last, to study the microstructure of 2 to 6% of copper and 0.5 to 1.5% magnesium addition in LM25. Next, the scope of study. Melting the LM25 billet with 2 to 6% of copper and 0.5 to 1.5% of magnesium alloy by using the electric resistant furnace. Next, preparing the sample by using an investment casting process. And lastly, analyze the morphology and microstructure by using the optical microscope and scanning electron microscopy testing. Okay, next we go to the literature review, which is the microstructure of a material is composed of different phases of variable form, size, and distribution, such as a grain, precipitates, dendrites, spherulites, lamellae, pores, and others. The phases are distinguished from other by their various crystalline, semi-crystalline, or amorphous structure when observed with an optical or electron microscope. Microstructure formation is strongly influenced by the amount of energy required to create new interface. This is what we can get from the microstructure morphology. This is include the defect, impurities, grain, and grain boundaries. Next, we will go to the journal and description of the author. First, from the Prasada Rao, cast LM25 alloy consists of long plate needle-like eutectic silicon particle in the interdendritic region of coarse alpha aluminum matrix with 0.2% master alloy for 5-minute holding. From Singh et al. 2016, T6 heat treatment produced by liquid metallurgical rod and found three phases in the microstructure are alpha aluminum primary, eutectic silicon, and magnesium silicon. From Liu 2020, his statement, which is A356 with 0.54 scramium alloys with heat treatment found the dark phase with ecogel morphology, alpha phase, gray phase, eutectic silicon with fibrous morphology, bright alloy, aluminum scramium, and silicon. Complex Chinese script-like morphology appeared. Next, Sakla Koklu, 2011. The primary aluminum Dendrite was composed of eutectic silicon particles which were present because of a high cooling rate and the low pouring temperature. Grain size of Ascas and T6 alloy are 147.2 micron and 144.4 micron, respectively, in expandable pattern shell casting process with vacuum and low pressure. This is statement from Jiang et al. At 2011. Lastly, the statement of Shabestari 2004. The copper content exceeding 2.5% is reducing eutectic temperature, which increase the range of the solidification and thus promote the formation of porosity. This is the project flowchart, which is we get a propeller information, get a LM25 billet, then go to melting process for doing investment casting, which is including the pattern creation, mold creation, melting and pouring, casting removal, and lastly for finishing inspection. Then we go through the heat treatment process, then microstructure preparation sample, then go to the metrographic study, which is we will use the microscope and scanning electron microscopy, and then get the result. We will go to the submission. Next, this is the existing propeller information, which is the table above is a chemical composition of standard cast copper alloy for propeller, and the table below is the mechanical properties of standard cast copper alloy for propellers. Next, before we running the testing, we need to go for the investment casting process. The investment casting process will follow the standard as required, such as ASTM A957 or A957M to perform the investment casting for alloy. First of all, we need to do a pattern creation, which is the mold are fabricated from a steel by using a CNC machine. The mold was already prepared by assistant engineer at the casting lab. Secondly, wax pattern 3. The wax design typically are inject and form as a single piece of a metal die. Wax are heat with 100 degrees Celsius to melt it. Wax is poured to the aluminum mold for getting the pattern. The mold creation. Wax pattern dip into the slurry of fine ceramic known as a zircon powder 200 mesh and mixed with the colloidal silica. The ratio mixing for this slurry are 3:1. The viscosity of slurry are measured with a Zancap. The ideal time for viscosity of the slurry between 40 seconds to 60 seconds. The process will repeat 8 to 15 layers until the shell is thick between 8 to 10 millimeter of thickness as possible to withstand the molten metal it meets. Next, we go through the dewaxing process, which is the temperature of the oven are set with 200 degrees Celsius and left for 40 minutes. The ceramic mold is heat about 600 to improve the mold, remove any residual wax or contaminants. Next, we go through the melt and pouring process. The LM25 billet was melted into the electric resistant furnace. Also, the LM25 with modified alloy of addition of copper and magnesium. The LM25 and addition of copper and magnesium blocks were rendered with thermal heat up from 700 degrees Celsius to 720 degrees Celsius for 1 hour. Next, the pouring process are done. We go to the casting removal. We remove with hammer, and then we get the finished product. After we get the finished product, we cut the sample with bandsaw for the experimental process. This is a T6 heat treatment. This is the parameter for T6 heat treatment. The process including the solution heat treatment, quenching in water, aging, and cool in room temperature. For the solution heat treatment is 540 degrees Celsius. The time taken is 8 hours. Quenching in water, just a temperature water. Then aging, the temperature is 150 degrees Celsius for 3 hours, and cool in room temperature between 20 to 22 degrees Celsius. Okay, next, this is the equipment that used for the metallography uh, testing or experiment, which is we use optical microscope and scanning electron microscopy. The metallography consists of the microscope study of the structural characteristic of a metal or an alloy. Metallography is a general study of the metal and their microstructure. Metallurgical microscope help in determining the grain size and size, shape, and distribution, phase and inclusion, mechanical and thermal treatment of the alloy. Next, we use a scanning electron microscopy. Image produced by SEM, the surface with focus beam of electron. Electron interact with the atom of the resulting various signal containing information about the surface topography, composition, and other properties. Electron beam scan in raster scan pattern, work wide range of pressure and temperature. Resolution is 1 micron. Characteristic can be detected such as a topography, surface features, texture, morphology, shape and size, composition and crystallographic range of atom. But unfortunately, in this experiment, the SEM are not included with the EDX testing. This is because the movement control order just happened and cannot enter the lab. Next, software. In this experiment, this is the software that used for collecting the data as shown in the figure. The software that perform are ImageJ and Minitab. ImageJ are used for gain the grain and porosity size. The result will appear when we click the measure button as shown in a picture. Next, the data then export to the Minitab software for gaining the histogram graph. The histogram can show us the frequency of the grain and porosity size. Okay, we'll go for the result. For the microstructural study of S-cast and heat-treated alloy of aluminum, copper, magnesium alloy, optical microscope was used. So this is the sample of the structure that captured under optical microscope. The specimen were ground with emery paper of different size, such as 400, 600, 800, and 1200. We will polish with the polishing agent and etch for metallographic analysis with scaleless region. Based on the picture, the researcher have found that aluminum, copper, magnesium alloy examined have dendrite cell structure. We can see that S-cast micrograph consists of aluminum solid dendrite as the primary phase on grey color, with the interdendrite space being filled by eutectic mixture. Phase 2 is the dark one. It can be intermetallic compound including aluminum magnesium 2 copper or magnesium copper 2, or alloying element, for example a copper and magnesium with one or more alloy elements such as aluminum 2 copper and aluminum 2 copper magnesium, depending on the alloy composition. In addition, we can see the typical hypoeutectic dendrite-like surface. In addition, we can see the typical hypoeutectic dendrite-like phase structure with a dark Si eutectic phase enclosed by the optic micrograph in the S-cast sample, with coarse eutectic missing phase. We can see at picture B, it shows the flake of silicon in the S-cast modified alloy. The primary alpha aluminum dendrite was composed of eutectic silicon particles which were present because of the high cooling rate and the low pouring temperature. In picture C, we can see that the T6 heat treatment was transformed flaky or lamellar silicon particle into spherical shape angular morphology. In the heat treatment solution, sample eutectic silicon particles have been fragmented and spheroidized, while silicon particles have been refined and the edge have a sharper angle than the cast alloy before heat treatment. Next, this is the average of grain area of motorboat propeller. As I mentioned earlier, the grain size was performed by the ImageJ software. From the graph, we can see the grain size area for the copper-based alloy motorboat propeller are 1912.3436 micrometer squared. Next, this is the average of the area of the grain size for non-heat treatment. Based on this graph, the largest area of grain is sample 10, while the smallest area of grain is on sample 8. Then, this is the graph for the average area of the grain size for T6 heat treatment. The graph shows the higher grain size also on sample 10, which it is the SCAS LM25 without the modification, while the smallest grain size is sample 8, which it is the modification of LM25 with 6% copper and 1.5% magnesium. Next, this is the visual for all of the sample surface that containing the porosity defect. The NHT is non-heat treatment and HT is a heat treatment. The porosity was observed at the center of the specimen. This is because the center of the surface will contribute the strength of the product. The porosity are studied to observe and prove the statement from the Shabby study 2004, where she indicated that copper content exceeding 2.5% is reducing eutectic temperature, which increase the range of solidification and thus promote the formation of porosity. Based on the graph shown, the largest area of porosity formed at the center of the surface area for non-heat treatment is the sample 4, while the smallest area of porosity is sample 8. Next, the largest area of porosity formed at the center of the surface area for heat treatment is sample 2, while the smallest area of porosity is sample 9. Based on the result, we found that there has opposite with the Shabestari statement. This is because of lack of method used in collecting the data or improper and inconsistent method while pouring the melting alloy to the mold. Okay, this is the result from the SEM, scanning electron microscopy. The result shows from the sample with SCAS with addition of 2% copper and 0.5% magnesium. At picture A is a T6 heat treatment, while in B non-heat treatment sample. Before that, I'm very apologize because the SEM result not included with the EDX analysis because of the movement control order for COVID-19, so I cannot enter the lab. So I will roughly explain the sample result based what I observed. Based on the picture, A is a heat treatment sample and figure B shows the non-heat treatment sample. The grain boundaries was found at 200 magnification. It was observed that the grain boundaries on a figure A more finer, while for non-heat treatment grain boundary structure are big and easy to slip and occur the material easy to break. Next, this is a Gantt chart for final year project 2. The flow from the research of information, collecting of data, analysis of data, data organizing, experimental and testing, chapter 4 result and discussion, chapter 5 conclusion and recommendation, report draft submission, project activities, presentation, and then report submission PSM2. For conclusion, the grain size of the propeller are coarser than modified alloy after heat treatment. The microstructure refinement are done by adding the percentage of copper and magnesium into the SCAS LM alloy, LM25 alloy. The addition of percentage of copper and magnesium was reduced the grain size. Grain size for modified alloy with non-heat treatment are coarser than modified alloy with T6 heat treatment. Heat treatment T6 was applied to reduce the grain size. The grain size are finer than SCAS and modified alloy SCAS LM25. This rise in porosity appears to have a close correlation with the formation of large volume of copper-rich interdendritic phase. Next, hardness tend to improve for multiple additional magnesium with increasing deformation. The higher the content of magnesium, the higher of hardness. Increasing of copper 2 to 6% and magnesium 0.5 to 1.5%. UTS and slight difference in aluminum LM25 alloy allocation and strength. This result from a partial alpha phase, aluminum dendrite refining, solid reinforcement of solution and hardness precipitation. The 6% copper and 1.5% magnesium addition to the LM25 alloy result in a maximum improvement in mechanical properties. The present study on mechanical properties for modified LM25 alloy show the sample 6, 7, and 8 after T6 heat treatment comply with the standard cast copper for propeller, and it can be replaced for aluminum-based alloy in propeller industry. For recommendation, it need to improve the studies on the morphological structure by using EDX and X-ray diffraction to get the detailed information of the chemical composition of the structure. Next, focus the study field on the shrinkage or solidification time that may influence to porosity of the copper and magnesium addition in LM35 alloy. Lastly, the facilities such as a machine and tools need to be improved in terms of the maintenance for each the student research. Lastly, this is the reference that involving in this research. The reference are mostly from a journal and article. That's all from me. Thank you.